This video is about ethers, so we'll do everything in this one: nomenclature, properties, synthesis, reactions, and it's not even that long. Okay, so first let's talk about the ether functional group. It is kind of similar to alcohol and water. So if you look at the ether group that I've shown here, it's ROR. So alcohols were ROH, water is usually HOH. So they're kind of similar, okay? And so the oxygen here is still sp3 and the bond angle is 109. And then ethers, it's a little bit more critical to talk about this because this gives them a little bit of a bent structure, and because they are bent, they will have different physical properties, okay? Because oxygen is still electronegative, so we'll talk about that also, okay? And just like we have thiols, which have sulfur, ethers also have a sulfur in it, and again, we're not doing it, but I just want you to know that it is possible to have sulfur instead of oxygen, and those compounds are called sulfides. So in the nomenclature of ethers, we're going to keep it pretty straightforward. The nice thing about ethers is that, you know, the name will end in ether, so that's a good thing. Ethers are what I call like the internal groups because they're always found in between two carbons. So the smallest ether possible is going to be CH3OCH3, which is dimethyl ether, and that's it. That's the only name. There is no like general name and IUPAC name for it. Okay, so that's it. Whatever is on either side of the oxygen is how you would name it. So just take it alphabetical with your usual rules. So in this case, where you have an ethyl group here and a methyl group here is ethyl methyl ether. Again, just alphabetical, okay? Keep it that way. And then if you have two ethyl groups, that would be then the diethyl ether. So you can keep going on and on, ethyl propyl ether, or any kinds of those ethers. If you have small groups on both sides, it's a lot easier. If you have larger groups, then things become different, okay? So for example, let's talk about this one here. And in this case, you still have, sort of groups that you can actually name this one. So this is, for example, sec-butyl group. This one is the methyl group, okay, over here. So you can call it sec-butyl methyl ether if you want to. Now, if you don't remember what the heck this is, I completely forgot. Oh my Lord, in those cases, you can treat this group as a substituent, okay, which is the ether group. So this is a small ether group, and this, because it's a methyl group attached to oxygen, it's called methoxy. So 1, 2, 3, 4. So on the second carbon, you have a methoxy group. So 2-methoxy, and then the long chain, parent chain, which is butane then. Okay, so you can name it that way also. 2-methoxybutane would be more like an IUPAC name. This one is more like a general name. You can give me either, it's fine. I can give you either as well. So anyhow, in this case, this group is called ethoxy group because there are two carbons in here. So ethoxy and then cyclohexane or cyclohexyl ethyl ether. Okay, so when you are using the ethoxy group as a substituent, then your base name is going to be whatever the alkene it's going to be. But if you're going to use your ether as your central point as your base name, then it's going to end in ether. Okay, here we have methylphenyl ether, methylphenyl ether. That's good enough for this one. And then here I've put numbers on so that you can see because it's a long chain. And here the main thing that I wanted to show you is that there is no preference for ethoxy, methoxy, or any of the alkoxy groups because they are just like any other substituent. There is no priority. So what you do is there is more branching on the left hand side. So you start numbering from here. Okay, on the left side, if there was more branching on the right hand side, you would do that. Okay, so here 1, 2, 3, 4. It is just normal. If you had any alkyl group here, it would be the same thing, right? So here again, take it alphabetical. So 3-chloro, and then 6-methoxy, and then the methyl, 2-methylheptane. Okay, so keep it simple. Now, because ethers are internal groups, you can also find them in a ring. Okay, so these are some of the common rings that you can find for ethers. Now, this is going to be the most common for us, epoxide, which is also called oxirane. And this is the smallest ring possible for an ether. This has very special properties, so we are going to do this on a separate presentation. We have a separate PowerPoint for this one. All others are just like a normal cyclic ether. Okay, this is 4-membered ring, 5-membered, 6, and then so on. There's not 7, but you have 2 ethers here. So the IUPAC names of these ones are a little bit different. Okay, so you can see that you have the ox in front of all of these names, and the ending is different. Okay, I don't expect you to remember any one of them except for oxirane. Okay, this is the most common one that you will find. And oxirane also, if you don't remember oxirane, it's fine. Epoxide. Okay, so epoxide is the one that we will cover also. And that's the one I recommend that you remember. All the other ones, you should be able to recognize it's an ether. If you don't remember the name, that's fine. Okay, and this one I want to kind of just mention to you. This is tetrahydrofuran. It's the 5-membered ring, and this is a very common solvent, okay, for ether. So this is another one that you should know. So just these two, okay, those are the common ones. So the physical properties of ethers, same things, the boiling points and solubility in water. Let's talk about this. So boiling points are low for ethers, and because there is no hydrogen bonding, there is just barely a little bit of dipole moment in there because of the bent structure of ethers. Okay, so I kind of mentioned that before. So where you have oxygen like this, so you have R and R, so you have some dipole moment. So because of that, ethers are slightly polar, but other than that, there is really not a whole lot going on for ethers. Okay, so they have low boiling points. Dimethyl ether, we don't really use that much because of that reason. It's just sort of a gas. And then diethyl ether is kind of a solvent that we use in labs, and that has also a low boiling point. Okay, so you can smell ethers in the lab if you go in, and when you smell something, it means that something is vaporizing all the time. So they have low boiling points, and as they get higher and higher molecular weight, then then the boiling point will increase. But the lower ones are really low. They have higher boiling points than alkane, but definitely lower than alcohol. Alcohol is hydrogen bonding, right? So that's really high. So here are some of the examples, okay, for the boiling point and dipole moment for all of these compounds. So you can see dimethyl ether, negatives. Yes, in diethyl ether is getting little positive, but 35 really, I mean, on a hot day, ether is boiling. Solubility in water is a little bit low. The smallest ethers, they also kind of dissolve. I mean, you can smell if you mix something in water. If you mix the ether in water, you can smell that, okay, ether was there, but otherwise they have no solubility because there's no hydrogen bonding going on. The slight polarity helps a little bit, but really no, not really too much. Because they're not soluble in water, when you talk about density, density is that they're lower than water. Okay, remember water is a beautiful number, 1 gram per milliliter. So, everything else can be compared to water. And also we use water a lot in the lab as solvent. So it's kind of nice to know whether my solvent that I'm going to add for organic, extractions or whatever, is it going to be on top of water or is it going to be below water, right? So in a separatory funnel, for example. So density is lower than water, so it's lighter. And then odor is actually quite pleasant, okay, for ethers. Now, you don't want to smell ethers too much because they can knock you out, but otherwise they don't have a bad odor, okay? But you can smell ether. You can tell, okay, it's been around, but that you've been around ether. But otherwise, it's not a bad smell. Applications of ethers, there are a few, okay, and so the one that I've been mentioning a lot here is a solvent, and ethers are the most common solvents, okay, and that's a good news sort of for us, because when we say something is a solvent, it means that they don't react, okay, which means what? It means that we will not be doing that many reactions of ethers, okay. That's why I only have this one PowerPoint for ethers, because there is really not a whole lot going on for ethers. So solvent means something that doesn't react and can carry on a reaction. Now ethers have a really good advantage for organic compounds because they have the slight polarity and they're also non-polar, so they can dissolve a lot of compounds. So they're really good. The only bad part about ethers, I would say, as a solvent is that some of them can have low boiling points, so you can't do reactions at a high temperature. So for that one, tetrahydrofuran is a good one. Remember, that's the cyclic one. So tetrahydrofuran THF is a good solvent in the labs. Very common to have that, as a solvent. The other application of ether is as crown ethers. These are some examples of crown ethers, the first two over here. And what crown ethers is that they create, I mean, first of all, it looks like a crown, right? Something you could wear on your head, provided that all these oxygens are jewels, But anyhow, so what they provide is this kind of a polar cavity in the middle, okay? And so these crown ethers can be used for a lot of things. They can be used to remove anything that is polar, or it can be used as something to supply something polar, okay? So for example, you can use them as phase transfer catalysts, okay? So catalyst in phase transfer means you're transferring things from one phase to another. So you can take the catalyst from a non-polar phase to a polar phase, okay? Or you can use it for trapping metals. In those cases, the crown ethers are called chelating agents. So here is an example that you need a small crown ether for a small cation and a large crown ether for a larger cation. Okay, so this is just an example. You can have different kind of cations being trapped in there. So that's a crown ether. Then the most common application of ethers is actually as an anesthetic agent, and anesthetic agents are something that put us out. And so some of these ethers are actually gases, and so these gases you can inhale them and then you're out completely. Okay, I don't want to get too much into the anesthetic agents because this is really a very complicated field, and also there are so many different kinds of anesthetic agents. The one that are topical, some things that you take them, inhale, things that you just inject in a small place. So like dentists use very topical small kind of anesthetic agents to say remove a tooth or something. So there are different kinds of anesthetic agents, but ethers were one of the first anesthetic agents to be used. Okay, before this there was like nothing for surgery. I mean, you can think about what was used as an anesthetic agent before ethers. You can email me if you know the answer. But anyhow, so it uses anesthetic agents, but they are toxic, and so now there are different kinds of anesthetic agents now. And then finally, epoxy ethers. Epoxy ethers are kind of polymers, and these are used as coating agents for a lot of things like metals and some wood also, to protect them from weathering. So it's really very, very practical things here. All right, so let's talk about synthesis. There are just like 2 or 3 syntheses for ethers, and the first one is called bimolecular dehydration, and really what it is taking 2 alcohols, treating them with sulfuric acid, and then you get the ether, okay, and then the water molecule. So it's a dehydration, so you're removing water in the process. So how does this work? Okay, so here is the mechanism for the reaction. You take alcohol, and of course in presence of acid you're going to protonate that alcohol. So that's protonated and then it's ready to leave, right? So the other alcohol molecule, another one that has not been protonated yet, will come in and attack this. So this is kind of like an SN2 reaction going on here. So this is attacking, and then the alcohol group is leaving. And then once you still have that proton on the oxygen here, so to relieve this oxonium ion, comes in another water molecule, picks up the proton. There you have the ether. Okay, so it's a good way to make an ether. The only thing is you have to do it step by step, because you don't want to protonate all the alcohol. You want to protonate only half of it. Okay, so the other half of it is added after a little while. So then you will still have some nucleophile left in there. So this is a good way to make an ether, but this is good only if you want to make a symmetrical ether, okay? Because, when you have sort of this kind of reaction going on, which is uncontrollable, if you try to make an asymmetric ether, then sometimes it will give you a mixture. Okay, so if you take ethanol and methanol to make ethyl methyl ether, then you can get all sorts of mixtures in here. Okay, and so it's not a good idea. But if you want to make something symmetric, then yeah, sure. Okay, not a problem at all. Or something cyclic also, okay, would be totally fine with this. So you have to kind of choose your synthesis according to its flaws, and what you want to make. So to make asymmetric ethers, then Williamson synthesis is used. Okay, and Williamson synthesis is a very common mechanism that you have done before, hopefully, in SN2. Okay, and SN2 is where you have a nucleophile and you have a substrate. Okay, so you have, and I've talked about this in alcohols also, where you take an alcohol, treat that with a strong base, you get an alkoxide. Once you have this nucleophile, now you can have a substrate with a leaving group and you get an SN2 reaction. Okay, so it's a very typical synthesis that we've been doing so far. And you generate an ether. This ether, you can see it's asymmetric now. Okay, and Williamson synthesis is actually quite good for making ethers if you wanted to. And where would you make ethers? I mean, like if you have a complex compound, then maybe you have an ether in there. Carbohydrates have a lot of alcohol, so you make ethers in there. So that's how you make ethers. But the main thing that I want to talk a little bit about here with the Williamson ether, because the synthesis is not difficult, okay? It's the retrosynthesis that we need to look at. So for example, if I were to ask you to make this ether and say, okay, give me, what kind of starting material you need for this. So which means that you're going to look at this ether and say, okay, what is my nucleophile and then what is my substrate? Okay, so the nucleophile is the negative one, obviously, and you can see from this synthesis, the negative is on oxygen. So it's the alkoxide, okay? And the substrate has the halide on it. So if you're cleaving over here for this ether, then the right-hand side fragment, that's the one that's going to be the oxide, and the left side fragment is going to be the halide. If you fragment on the right-hand side for this ether, then the left-hand side is going to be the alkoxide, and then the right-hand side is going to be the alkyl halide. So substrate, nucleophile, substrate, nucleophile. Okay, fine. Okay, what are we trying to prove here? Number one, that you have different ways of making an ether. Okay, for a Williamson ether, because it's asymmetric, there are two different ways of making an ether. Now the question is, okay, which one is better then? Okay, so is it like both of them, are they the same, or are they going to be one better than the other to make an ether? So then you have to say, okay, if I'm doing this kind of a synthesis, this is an SN2 mechanism. So what are the conditions that you need to have a good SN2 reaction? Well, the most important thing is you need a primary halide and you need a strong nucleophile. Strong nucleophile is not a problem, okay? So the primary nucleophile here, this is a primary nucleophile, substrate. And then here with the cyclopentane, the bromocyclopentane, this is a secondary substrate. Okay, so secondary substrate sometimes can do eliminations also, okay, especially with some nucleophiles. In this case, very honestly speaking, both are quite okay, because the main thing about the secondary halide is it sterically hindered? It is not sterically hindered. Okay, it's easily accessible because the cyclopentane is kind of planar, so it's easily accessible, this carbon, okay, over here. So yeah, very easily you can do SN2, and this one is not even a problem because primary halides can do SN2 very quickly. Okay, so neither of these is really an issue. Okay, so you can do either of these ones. But where is an issue? Okay, so let's look at this kind of an ether where you have different kinds of groups on both sides and a little bit of a crowded, okay, ether that we have here. So this ether you can again cleave on either side of the oxygen, okay, and unless something is symmetrical, you have two options, okay, in there. For a symmetrical ether, only one cleavage is enough. But in this case, where you have asymmetric ethers, you will always have two choices. Okay, so if you cleave on the right hand side, then the left hand side is the one with the nucleophile. The right hand one is the alkyl halide, okay, and the substrate. In the second part, if you cleave on the left hand side, then your halide is on the left one and the right hand is the oxide. Okay, that is the nucleophile. Now, when you look at these two, when you compare these two, things are a little bit different. Okay, why so? Is because on the first retrosynthesis, you have a primary halide, but in the second retrosynthesis, you actually have a tertiary halide. In this kind of a tertiary, a secondary halide, but the secondary halide is quite sterically hindered, okay? And the nucleophile is small, okay? It's not really huge, okay? Because sometimes when you have bulky nucleophiles, they have a hard time getting to the electrophile. But here is not such a big nucleophile, but still, there is a chance that instead of doing an SN2, okay, which just would be a normal SN2, right, where you have this attacking here and the bromine leaving, this would be a normal kind of a reaction, but instead you end up getting a little bit of E2 mechanism, okay, which means that you end up getting an alkene. So in Williamson synthesis, you kind of have to look at your ether and then decide which kind of synthesis is going to be good for you, okay? When you do the retrosynthesis, both of these may not be good for you. So then the last synthesis for ethers is alkoxymercuration, demercuration. We did this also for alcohols. And here you have the same reagent, which is mercury diacetate. So you can use this. Instead of using water now, we use an alcohol. We still start with an alkene, okay? So alkenes is still our starting materials. The mercury acetate is still there, sodium borohydride is still there, but here, instead of water, you have an alcohol. Whatever alcohol you have is the kind of ether you will make. Okay, so this was methanol. Here we are using ethanol, and so this we got as ethoxy. Okay, so this is a very nice synthesis. No issues over here, no problems for elimination or anything like that. The only thing here, it's going to be Markovnikov. Okay, that's why you got the ether on this carbon and not on the primary carbon. So that's the only thing, but other than that, it's a nice synthesis. So the reaction of ethers is only one reaction of ether. Okay, as I said, ethers don't really do a whole lot of reactions because they are very unreactive. That's it. Okay, that's my really great philosophy there. But anyhow, so the only reaction they do is acidic cleavage, which really is breaking apart of an ether. So an ether will break apart to give you two alkyl halides. This is generally going to be an acidic mechanism. So an acidic mechanism meaning that you're dealing with something like hydrochloric acid or hydrobromic acid. So this is not like sulfuric acid reaction, okay? So when you do this kind of a cleavage, you end up getting alkyl halides as products. So I mean, this is not really a reaction you would want to do, but this is a reaction that can happen in case you're doing a reaction with something else and you're using ether as a solvent. Do you see what I'm talking about? So if you have another reaction going on and you're using ether as a solvent and you're using hydrochloric acid, you got to watch out because then ethers will also start reacting, okay, over here. So you have to be careful with that. Okay, so anyhow, how does this work? Okay, so here the ether is actually the nucleophile, the oxygen, and then oxygen will pick up a proton and become protonated. So once it's protonated, now the oxonium ion becomes a good leaving group, right? So then SN2 reaction happens. The chloride of the HCl that was as a not leaving group per se, but it's there, so that happened. But anyhow, so the chloride is there. The chloride now is going to do an SN2 reaction and this group leaves, which is now the alcohol group. Okay, so right here, all of this alcohol has gone now, and here you form one alkyl halide. The reaction doesn't stop here. The reaction continues on when the alcohol will then attack or it will not attack, it will protonate, with the other HCl, so it will kind of attack the proton anyway. So then it'll get protonated. Now this reaction we have already done in alcohols, okay, so you might remember that this is more like an SN2 reaction, and then you will get the alkyl halide here, okay. So this kind of a reaction is quite common with ethers, and this is really the only reaction that we do. So I think I have another mechanism for you. Yeah, so here if you had a cyclic compound, the first one was where you got two fragments, and in this one, if you have a cyclic ether and then you start doing the mechanism for this one, you will end up with an ether, not an ether, an alkyl halide or a dihalide. Okay, so here you have two halides here. So again, protonation, and then the bromide comes in, attacks here. Remember, it's not going to attack the oxygen, okay? Oxygen is positive, is ready to leave right now. Oxygen has 3 bonds, cannot have any more. So don't attack the oxygen. So this is the electrophile right now. So bromide will attack here. This bond opens up. So then you end up getting that alcohol, but the alcohol is not leaving anywhere. It's still there because everything is still connected, okay, to the same compound. So then you have the alkyl halide here, but the second alcohol that was there that you just generated is going to do the reaction, and now again with another SN2, that's how you get the two halides on there. Okay, so I've just kind of made this in a straight chain. So that's it, as far as the acidic cleavage is concerned, then this is the only thing. So, and that's really the only reaction we have for ethers. So that's it for ethers. Okay, nomenclature, some physical properties, the synthesis, the 3 syntheses that we did, not just the Williamson, that's the main synthesis. But we have all the other syntheses also for ethers, and then the acidic cleavage mechanism.